Hey guys, this is Shawn, and today I wanted to make a video defining symmetry elements perpendicular to the plane of a planar molecule. I wanted to start this video off talking about the learning goals I've set for this video. The first one is to have a foundational understanding of symmetry and understand how symmetry relates to chemistry, and then lastly know examples of planar molecule symmetry. Before I get any deeper into the video, I want to make sure my audience has a clear understanding of what symmetry is. Symmetry is the quality of being made up of exactly similar parts facing each other around an axis. But the big question is, how does symmetry relate to chemistry? So I already mentioned symmetry, but when you throw chemistry into the equation, you get something called molecular symmetry. And basically what this is it's a way to group molecules according to symmetry. And this is very helpful because you can predict many of the molecules' chemical properties. And the picture to your right, it just shows various molecules. There's water, there's benzene in there, and just some of the basic molecules, and just showing off their symmetry properties. I want to take a brief moment and explain the historical background and how it relates to molecular symmetry. The first scientist I would like to mention is Eugene Wigner. Wigner used group theory to explain rules for atomic spectroscopy. He received a Nobel Peace Prize for physics in 1963 for his fundamental symmetry principles. And next is Hans Bethe. He used point groups to study Lagrange field theory in 1929. And Lagrange field theory, I can make a whole other video explaining it, but just know that these two people, they are important in their role for molecular symmetry. So I mentioned planar molecules in the beginning of my video, but I just want to make it clear that my audience understands what a planar molecule actually is. So a planar molecule, it's very easy. It just has all its atoms lie on the same plane. So as you can see, this is benzene. It's a solid example of what a planar molecule is. And as you can see in the 3D image on the top, all the atoms are on the same plane, and below is just the structure of it with sticks and line diagram. And it's a very straightforward concept, but is a vital piece of information to understand what I'm about to explain in the future slides. So the whole reason behind this video is to define symmetry operations that are perpendicular to the plane of a planar molecule. So for the first operation, I want to talk about an n-fold axis of symmetry, and this is denoted by C subscript of n, where n represents an integer. And for the example I'm going to use is BF3, which is boron trifluoride, and in this example, n equals 3. And so the equation is 360 degrees divided by n, and since n equals 3, it's 360 divided by 3. And this is used to determine your bond angle, which is 120 degrees. And as you can see in the picture to the right, it clearly demonstrates that it's 120 degrees. And the picture to the left was added just to get a deeper understanding, because I feel like 3D models help visualize better, at least for me. And this is a case of a molecule containing a plane that is perpendicular to the molecule. The next symmetry operation I would like to mention is called the plane of symmetry, and this is denoted by a lowercase sigma. And it's also to note that this leaves a molecule looking the same, so nothing changes with it. And basically what this is a perpendicular plane. It's called a horizontal mirror plane, and it's denoted by a sigma subscript h. And I've given some examples here. The middle is H2O, and I believe the left is boron trifluoride. And as you can see, the plane, it dissects perpendicular at right angles to the planar molecules. Last operation I'd like to touch on is center of inversion symmetry, and this is denoted by a lowercase I. And then this is a very easy one. It's inversion through the center of a molecule, and it also leaves a molecule unchanged. And as you can see in the example, this is benzene again, and as you can see the green dot, that typically represents the center of inversion. So I've been explaining all these symmetry elements, but you're probably wondering, why is there a need to recognize these? And the first one is it helps to construct molecular and hybrid orbitals. So an orbital is basically a mathematical function that can be used to describe the molecule's wave-like features. Using this information, you can determine physical and chemical properties. Next is it helps interpret spectroscopic, which is vibrational and electronic properties. And lastly, it helps determine the chirality of a molecule. A chiral object is one that is said to be distinguishable from its mirror image. So an easy example is your hand, left and right hand. They're mirror images, but when you superimpose them, they do not match up. Thank you for watching the video. I hope you were able to learn something new, and have a great day.